Rahim. Hello students, welcome to the Electrical Engineering channel. In this lecture, I am going to start the 8th chapter of the Engineering Electromagnetics textbook, and the name of this chapter is the Steady Magnetic Field. And in this chapter, we will discuss the laws associated with the magnetic field. And the magnetic field can be defined as the field due to a moving charge, and the fundamental law in electrodynamics is the Biot-Savart's law, and Biot-Savart's law can be stated as the magnitude of magnetic field intensity at point P due to a differential length dl is proportional to the product of current and dl and sine of the angle between dl and a line joining dl and P. And the magnitude of magnetic field intensity is inversely proportional to the square of the distance between P and dl. So this law is similar to Coulomb's law in electrostatics, and according to Biot-Savart's law, you can see in this figure the magnetic field intensity at this point P is proportional to the product of the magnitude of current, length of this differential element, and sine of this angle. So this is the angle between dl and this position vector r. So r is the vector between this differential length dl and this point P. So the sine of this angle will be involved in this expression, and the magnetic field intensity at this point is inversely proportional to the square of this distance. So this distance is r, so it is inversely proportional to r square. So when we remove this proportionality, we have to introduce a constant, and that constant is equal to 1 by 4 pi. So dh will be equal to 1 by 4 pi idl sine theta divided by r square, and ideal sine theta can be written as ideal cross ar, and ar is the unit vector in the direction of this r vector, and this can be further written as ideal cross r vector divided by 4 by r cube. So this unit vector can be written as r vector over r magnitude, and the unit of magnetic field intensity is ampere per meter, right? Because we have ampere over here. dl is in meters, r is in meters, and this is 1 over meter cube. So meter square over meter cube is ampere per meters. So this thing can be written as the total magnetic field intensity equal to the integral, line integral of this expression. And we have a closed integral because current always flows in a closed path. So when we have a line current, or we have a current passing through a line or a wire, then we will use this expression. But current can have other types of distributions as well. For example, in electrostatics, we had surface charge distribution and volume charge distribution. So that same distribution can also occur for the case of current. So I is the current flowing in a line or a wire. So this is the current, or this is also called a line current, and the units of line current are equal to amperes. The surface current density is represented by the symbol of K, and K is actually the current flowing through a surface, and this is the surface, and the width of the surface is equal to B, and the current is flowing through the surface, and it is crossing this width of the surface, which is B. So the surface current density is actually equal to current per unit length or current per unit width. So it will involve the length of the edge from where the current is crossing, right? So current is flowing in this direction and it is crossing this line. So the width B is actually crossed by this current. So surface current density will be equal to current per unit length, and that will be equal to current divided by the width of this surface, and width is equal to B. So K is equal to I over B, and total current I will be equal to KB in this case. And in general, I can be written as K multiplied by dN, and the integral. So dN is the edge which is normal to the flow of current, and the units of surface current density is ampere per meter, right? So this is very important thing. Similarly, another current distribution is called volume current distribution. So you can see in this figure that the current is distributed over a volume, and now in this case the current is flowing through the volume, but it is crossing this surface. So this is the surface which is actually crossed by the current. So volume current density can be defined as the current per unit area, and area will be the area of the surface which is being crossed by the current. And in this case, if we have one side as A and the other side as B, so the crossing area of this surface will be equal to A into B. So in this case, volume current density is equal to current per unit area, which it is equal to I over AB. And it can also be written as I is equal to J dot ds. Again, this will be the normal surface, or the surface which is present normal to the flow of current. So the unit vector of the surface is also normal to the current. So in this case, the direction of this surface and the direction of current will be in the same direction. So that's why we have to use a dot product over here. And IDL is equal to KDS is equal to JdV. So in Biot Savart's law, we have IDL, and IDL has the units of ampere meters. Similarly, if we have KDS, so K has the unit of ampere per meter, and DS has the units of meter square. So KDS will also have the unit of ampere meter, and JdV will also have the unit of ampere meter, because J is ampere per meter square and dV has a unit of meter cube, so it will also be ampere meter. So if we have such distributions, surface current distribution or volume current distribution, we can still apply Biot-Savart's law, and in that case we will use this expression for the surface current distribution. Here we will have current, which is surface current density. So K cross A R ds divided by 4 pi r square, rest will be the same. And for a volume current distribution, H will be equal to J cross A R dV divided by 4 pi r square. So for this case, when we have a current passing through a wire or through a line, uh, we can uh, derive the expression for magnetic field intensity when the current is flowing across the z-axis from minus infinity to plus infinity. So for an infinite line segment carrying a current of I, we can calculate the magnetic field intensity at any point. So in this case, you can see this is the differential element, because the current is flowing along the z-axis from minus infinity to plus infinity. The magnitude of current is I. So this will be our dl, and this is the point at which we want to calculate the magnetic field intensity. So the coordinates or position vector of this point will be rho a rho, and this the position vector of this differential element is actually z a z. So r vector, this r vector will be equal to rho a rho minus z a z, and the unit vector ar will be equal to rho a rho minus z a z divided by rho square plus z square under root. And this differential length dl is equal to dzaz, and dh is equal to idz. And so this is idl, which is dzaz cross ar divided by r vector. So ar is equal to r vector divided by r magnitude, and this is r square. So this will become I dzaz cross rho a rho minus zaz divided by 4 pi rho square plus z square raised to power 3 by 2. And we can evaluate this cross product, and we can then evaluate this infinite integral. And az cross az will be equal to 0, and az cross a rho is equal to a phi. So it will become I rho a phi dz divided by 4 by rho square plus z square power 3 by 2. So this will be our final form of the integral, and this integration is equal to 2 over rho square, and this same integration was performed while we were evaluating electric field due to a line charge. So I have written this expression directly. This is the same expression which we used for this derivation. So when we put this value over here, we will get H equal to I over 2 pi rho A phi. So it means that the magnetic field intensity is proportional to the distance for an infinite line segment carrying a current I, and the direction of the magnetic field is in the phi axis, is along the phi axis, and it means that the magnetic field lines are circular in nature, because phi is actually the angle. And This figure will clarify the this meaning of this expression. So here we have the infinite line segment which is carrying a current I. So this dot, and this figure is actually drawn using the top view of this arrangement. And if we see this figure from the top, we will just see a point uh, representing the line or wire carrying a current I, and around this current carrying conductor we will have magnetic field lines which are circular in nature, and the magnetic field intensity is also decreasing as we move away from this source. So at this uh, surface, so here the magnetic field intensity is stronger, and as we move away from the source, the magnetic field lines are becoming weaker. And here you can see we have dashed lines, and here we have sparse dashed lines. It means the magnetic field intensity is decreasing. So magnetic field lines are circular, that is along A phi, and H field decreases as the distance from the source increases. So if we have a finite length filament or finite length of wire which is carrying a current I, then what will be the magnetic field intensity? So in this case, we want to measure the magnetic field at this point, and the position vector of this point is actually equal to rho. So this is rho, and this is uh, one position vector, and this is the other position vector. So if we integrate our magnetic field expression from z1 to z2 instead of minus infinity to infinity, we will get the expression for magnetic field intensity due to a finite length segment. So same current I is flowing in this direction, which is upward, and now we have to define two angles. So this is angle alpha 1, which is being made with this point z1, and this is angle alpha 2, and this alpha 2 is the angle which this line is making, this row vector is making with this vector. So that vector is actually terminating at this point z2. So from here z1 is equal to rho tangent alpha 1, and z2 is equal to rho tangent alpha 2. So h will be equal to integral I dl cross AR divided by 4 pi r square from z1 to z2. Let's put the value of z1 and z2 in this expression, and here we will have the same expression, and this integration will be evaluated, and it will be equal to I over 4 pi rho z a phi divided by rho square plus z square under root, and we will put the limits from rho tangent alpha 1 up to rho tangent alpha 2. So while solving this integration, you can seek the help from the derivation which was done to evaluate electric field due to a line charge in my previous videos. Okay, so then you will see this expression as well. And in this expression, we have to put this limit. So after putting this limit, we will get this expression, and 1 plus tangent square alpha is equal to secant square alpha. And when we take the square root, it will become secant alpha 2. So tangent alpha 2 divided by secant alpha 2 is equal to sine alpha 2. So it will become I over 4 pi rho sine alpha 2 minus sine alpha 1, and this is unit vector a phi. So that is the expression of magnetic field intensity for a finite length current carrying conductor, and for an infinite current carrying conductor the magnetic field intensity is equal to this expression. Now I will solve a simple example, and in this example we are given I delta L, and it is equal to 2 pi az microampere meters. We are given 2 points P1 and P2, and we have to calculate delta H2. Delta H2 means incremental magnetic field intensity at point P2, and that will be equal to I delta L cross AR12 divided by 4 pi R12. So let's first evaluate R12 vector, and it will be equal to P2 minus P1, and AR12 is the unit vector, and that will be equal to this unit vector. And let's put this value in this expression. So IDL is equal to 2 pi into 10 to minus 6 AZ cross 4 plus 2 minus 2. So 4 plus 2 minus 2 divided by 24 square root, and 4 by R12 square. So R12 magnitude square is equal to 24. And let's evaluate this cross product. And to evaluate this cross product, we will use this determinant. and in determinant we will write ax ay az. This is az, which is 0 0 1, and this is our second vector 4 2 minus 2. So let's evaluate the determinant, and after evaluation we will get minus 2ax plus 4ay. That is the determinant, and let's put this value over here, and after doing the simplification we will get this answer. So that is actually the incremental magnetic field intensity delta H2 at point P2. So hopefully you have understood the basic concepts of Biot Savart's law, current distributions, magnetic field intensity, and for watching more lectures please subscribe this channel. Until the next lecture, it's goodbye.